session. So first, let us before starting on, let's just recap what we learned yesterday. So again, if you could put me the topics we discussed yesterday one by one, so that I'm sure that you remember yesterday whatever we taught you, the prerequisites. Mainly we discussed about the combinational circuits, like how does an adder, subtractor, mux, demux, and registers flip-flop works. And also one of the main things for prerequisite for the SAP was the bus architecture we built yesterday. This one, right? So we saw how to transfer the data between the bus from register A to register B, or when we come across contention state errors, we just went through that. So keeping all these in mind, let's move on to our actual session today. So this is done. And so as I presented yesterday, this is the block diagram for SAP1. So you need not worry. Okay, this is how it's gonna work and stuff. Let me just to build your curiosity even more, I'll be presenting the end result what we'll be building if you attend tomorrow's sessions as well. So as you can see here, this is the same diagram I just showed you, the blocks thingy, how you will be building this in circuit bus. So as you can see, I've disabled the clock here. So as you can see here, what this circuit now is going to perform is add these data 5 and 1 and store in the output register, and the output will be visible here. So let's check that fast. I'll enable the clock, and you can see it's working. I'm sorry, it's going to subtract here. As you can see, the sub control, it's 1. If it's 0, it's going to add. If it's 1, it's going to subtract. So 5 minus 1 is 4. You can see here it's done. Else, if I just give 0 here, you'll get the output as 6. So that's how simple it is. So coming back to this diagram, today what we'll be doing is one by one we'll see how to implement each block in circuit bus, and what the exact circuit you saw today, how to understand properly how it works and stuff. So to give a brief overview, like sequentially how the data proceeds in this circuit, what is the first block you can see here is the program counter. So what does program counter do? It points to the next instruction which is supposed to be executed in your computer. So after your computer is done finishing the current program, it knows what should be done next. So that's the role of a program counter. And input and MAR. So input MAR, in its input, it gets input as the address of its data. So let's, as you saw before, 5 and 1 was our data, right? So this input MAR block gets what is the address of those data. So that address is taken from this bus, and it shoves it into the RAM, and RAM outputs like what data was present in that exact address that's there. And instruction register that carries what is the current instruction being performed. So let's say in assembly I gave add R1 and R2. So that whole instruction which is being performed currently, that will be in the instruction register. And this is the most the interesting part or the intelligent part of the whole system, the controller and the sequencer system. So you saw yesterday, right? The control bits has to be exactly 1 and 0 to make sure only one block is outputting its data. So it has to be, so all these control bits you can see, CP, EP, these CE bar, all these 12 bits has to be controlled very logically, very efficiently. So control sequence sees that for you. So when you say add R1 R2, at from the time the program is loaded from the instruction register and MAR to the binary display, how in each clock cycle what bit should be set to 0 and what bits should be set to 1, that is taken care by the controller sequencer. Then accumulator, before that adder subtractor, you can see here. So it gets both one of its operands from accumulator and the other from register. This is the output register part. So let's say, as you saw in the circuit, we had connected it to an number display, right? So it could be that, or it could be an LED or a buzzer, any sort of such device which outputs the output. Yeah. And this is the pretty much like what each block is supposed to do. Do you have any other doubts till now? So first, let's see how to build this program counter right now. So everyone, go to your circuitworks account which you created yesterday. So let me also go back where we were yesterday. So this is what we had done. So to create a new one, let's click this plus, and this is going to be a program counter. Yeah. So you can see, right? If you want to see your saved circuit, just go to my dashboard under your profile, and in your saved circuits you could see whatever you called it yesterday. So let's start building this. So what your program counter does, basically it counts from let's see first of all, what does a program counter do. So basically it's a 4-bit counter. Counter are just, if you saw your digital design textbook and stuff, a block of registers aligned in a certain sequence. Its job is to count from 0 to 1. So 4-bit means the maximum it can count till 0 to 15, right? This is 0 to 15. So that's what it's supposed to do. And the output is the address of the instruction to be executed. So what this actually means is, let's see here. So this program counter puts its address on the address bus of the circuit, and this is loaded to the MAR. So you can see here, right, in the memory part, it's written here 0, 8 and 2, 9. So this 8 here is the address of the data. It's the address of the data which is stored here. So you can see, right, one operand is stored at 8 here. That's why I have 8, and the other part is like the immediate part is 9. So that's why you have the output 9 here. So don't worry about the 0 and the 2 part for now. As I mentioned yesterday, bus is split into 2 bus. One will be for the address and one will be the opcode, or else when you say, again, taking the same example, add R1 and R2, the add command, how is your circuit supposed to know that that it should add that? Add command, that is the first bit. So yeah, don't care about for that right now. So this instruction, the program counter, basically it puts out this 8 and 9 on the bus, and that is captured by MAR, and that is sent to the memory to get our address out. And then we told, right, so the program, it will be here and it will be loaded to the MAR. So that's about the program counter for working. Let's go and actually build this. Yeah. So for that, first we'll take an okay, sorry, re flip flop here, and an adder. So yeah, as mentioned again, if you just get confused what are these, just hover around this, it will show you this is Q, and you can see this is the A. So I'll connect this with this. Yeah, that is done. And so one of our input to the adder, okay, I'm sorry, so this is supposed to come behind. Mm. Huh. Okay. Then one of our inputs will be a constant number 1. So since it's an 8-bit one, this since yeah, due to the bus being divided, this will be of 4-bit. Let's make it 4-bit, and our since it's 4-bit, our input is also going to be 4-bit, and even our register is going to be 4-bit. So let's make this 1 and give it to our adder, but not this one. Yeah. Okay. So so the other input for the adder, it comes from so it basically comes from the output of the D register. In a moment, I'll explain why this particular architecture is being followed. So that is there, and we'll set our control bits. So this is to enable the register. Yeah, cool. And this was set to 0. And again, to control that when this output of this program counter should be and should not be on the bus, obviously we have to use a tri-state register to control that. So let's put that, and so let's make this also 4-bit, or else as you saw yesterday, you'll get an error, a bit width error. So usually when you see something like a bit width error, this is what would have usually gone wrong. I mean, yeah. Let's make this also 4-bit. Okay, cool. Let's give a clock to this. Okay, so how many of you are following with me? Just let me know in the chat box again. If I should slow down, or if it's too fast, just let me know. Okay, so let's name them according to our convenience. This is our output enable. So from this we can decide, as I told before, it should be on the bus or not. This is the count enable. So basically you can decide when you want your program count to start counting. And this is your input. So yeah, everyone have built this circuit. Okay, one is adder and the other is flipper. Yeah, you can see this is the adder, the 4-bit adder, and this is a D flip flop. Yeah. Yeah, the 4-bit component next to tri-state. Yeah, this is the output part. You can see. Make sure you make this a 4-bit as well. So I'll just repeat again. This is the 4-bit input. This is the adder. This is the D flip flop. This is the tri-state output. And again, you can find it in their subsequent sections. Yeah. If everyone are done with the circuit, I'll explain how this works actually. By the time, let's name this also. Let's keep this as output. And this input, it's going to be constantly 1. So for our convenience, let's name it constant 1. So let's change this back to 1 again. Yeah, and if you want, you can give the clear output as well. Will not be here using here, but just in case for any other purpose. So if you if you forgot something like how to shift this dot thingy, so that it looks more clean in your circuit, go to properties orientation, click up here, and just connect this. Yeah, good to go. Yeah, this is the clear one. So yeah, as I mentioned before, basically what's the function or what is it supposed to do as a program counter? It's just supposed to count from, since it's a 4-bit, from 0 to 15, right? So let's make the circuit do that. How? So you can see here first, it's the adder. What's the job of an adder? Whatever input you give it to its A terminal and B terminal, it's just going to add and give its output in the sum terminal, right? As you can see, the sum. So for one, I have given for one of its B input, I've given 1 as its input, and for the other, I've given the output of this D flip flop. So why is that? Because every time the clock it's done with its input. So let's see. So it was 1 here, and before, as you saw, before the clock it was 2. So 2 plus 1 will return 3, and that 3 is being stored here. So again, in the next cycle, one of its input will be 1, and the other input, you can see here, it's coming from the D flip flop output, and circuit was clearly shows what it's being stored there. So it's 3. So 3 plus 1, 4. So again, this cycle keeps continuing. So when you reach okay, again 5, 6, 7, 8, 9, the decimal coding. So yeah, after you have reached 1 year, so how does it set back to 0? If you add 111 after 15 plus 1, it's basically going to overflow, and it's going to set back from 1. Or in simple words, 1 plus 1 is 0, right? And that 1 gets carry over. So 1 plus 1 0. So that way, everything here becomes 0, and that carry bit or the overflow, that gets just discarded. So that's how it works here. Yeah, I'm sorry, this was not showing. So just let's do this again. Yeah, so as you can see here, I'll just repeat it quickly. The output of D register, this is going back to the adder, right? You can see here. So, and one of its input is B, that's constant 1. So 0 plus 1, what's the job of adder again? It has to add. So after 1 pulse, 1 gets stored here. And for the next circle, it's 1 again, and the other input for this is the value stored in this register, because that is what is given to its output. So again, 1 plus 1, it's going to become 2. Yeah, so that's how it does. Then if you add 15 plus, basically 111 plus 1 is going to overflow and reset back to 0. So yeah, again, so that's how it works here. Yeah. Any doubts with this circuit working? How or where, by anything? So I yeah, and we really want you to build the last circuit we showed because that's really cool. So make sure to let us know then and there when you didn't understand anything I'm building. So just let me know, or if I have to repeat, I'd be glad to. Okay, let's not give this a clock here because while instantiating, it might be a problem. Don't worry about this right now. And this is going to be clock. Yeah. So you can see something as edit layout right here. Yeah. So when you, so obviously if you try to build all these so obviously if you try to build all these circuits again, your circuit, the whole, it's going to look super messy. So it's better to instantiate that. So we'll see how to do that. We'll go to edit layout. You can play with this, how you want your circuit to look. So I'll increase the width here. It's the output one. And yeah, this looks good to me right now. Let me just okay, move the title to 1. And yeah, that's it. It's good to go. Here, another thing, don't use Control S. It's not going to be, just exclusively click save on this. Yeah. So this is done. So let's go to our main circuit and insert this circuit here. So before that, we'll be using a clock and a clear, right? So we'll just do that. Let's draw our bus also here before we get into it. Yeah. Another, let's name this clock, and another input clear. Yeah. So let's instantiate. How do you do that? Just right click on the plain circuit here, and you can see here insert sub circuit, right? So just click on that. You can see we have built, we have 2 other files right now. We want to bring the program counter. So just click on that and click insert circuit, and yay, we got one. So you saw in the architecture, right? The program counter was the top leftmost one. So this is how it's going to be. You can keep the okay. You can give the clear here, and constant one also. Let's make this 4-bit one, and yeah. Okay, and the output, it's going to output the address. So let's give that, and our input to control our output enable. This is the uh, enable part, and yeah, so this part is ready for now. Any doubts till now? So we are done with the program counter part. How do I get the PC to the main screen? So when you create a new project, by default this main uh, page is going to be there, right? So just click on anywhere with the plain background, uh, right click, insert sub circuit, and click on program counter, and click on insert sub circuit. You have it here. I guess that was your doubt. So since we are done with the program counter, yeah, before we build the adder and subtractor part, let's see how actually subtraction takes place. I know that you know. Um, just a quick recap. So let's say 5 and minus 2. So take 2's complement of the subprime. So basically take 2's complement of the minus 2 and add it with the minor. So whatever the output is of the minus 2, add it with 5, and whatever the addition result is, that's your answer. So that's how simple it is. So yeah, that's how you subtract. And let's see what are your function and what features your adder subtractor block should possess. For that, first one performs addition and subtraction on 8-bit binary data. Yeah, since it's happen like as the name suggests, simple as possible, and that too the first, like the first part of it, it just can add and subtract. So as you saw before, it has this control signal called sub add. So if you keep it as 0, it's going to add. If you keep it as 1, it's going to subtract. Yeah, that's what it should have. And one input is taken from the accumulator. Yeah, as I maybe I could go back here and so as you can see, right, this SU thing, this is what I mentioned to control whether it should add or subtract. And one operand, it's taken from the accumulator. Where does accumulator get from? It gets it from the RAM. RAM throws it on the bus, and accumulator picks it up. And the same way, B register also get its data from the RAM, and yeah, basically 5 and minus 2, 5 will come here, let's say minus 2 will come here. So the block got its operands. So coming back, uh, yeah, the other from the B register. And adder and subtractor, since it's a combinational circuit, and it doesn't have any clock or such sort of things. So as soon as it gets it sorry, as soon as it gets its operand, the the output will be immediately ready. You don't have to give the input enable or such sort of thing. So whether you have to put it on the bus or not, that depends on the output enable control bit that you can control. But the output is it gets calculated immediately. So that's one of the points. And you can control the data going in and out through the control signals. Yeah, so basically when so because as soon as the B register gets loaded, that automatically reflects in the adder subtractor block. So you might want to be careful what value is stored in your accumulator and B register. So for that, you always have your control bits. So this was the yeah, this is what it's supposed to have. So let's say if it's a human, you say it's supposed to have 2 eyes, 2 legs. So that's how it is. This is supposed to have these. Yeah, this was a brief one. We'll also be building this circuit now. Yeah, since time is we were running a little slow. We'll do it. So let's call this adder subtractor. So just let's take 2 marks here. Again, make sure you make this as 4 bits. This is 4 bit. Okay. So, yeah. Just keep doing the connections with me. Once it's done, I'll explain you. So you do not need to build your two complements in the miscellaneous, or you can even search, but I don't know, I'm lazy to search. I kind of, yeah. So let's connect this with this and this with this. Huh. And let's get an adder here. Make this also 4-bit array. Yeah. So one of its output is going to be this, or no, let's make it. Huh. Yeah, I'm sorry. Yeah, since it's an 8-bit, yeah, as I mentioned before, it can calculate up to 8-bit. So yeah, sorry for the confusion. So if it was a 16-bit, it would do its calculation in. Yeah, again, it's showing red mark because you make sure even the 2's complement, it's in the correct bit width. So I think let's take a new one. I don't know, I made some. Yeah. And let's give it to this array. Cool. So now we'll give our both inputs A. This is also 8-bit, and yeah. Oh. And let's just by the time any doubts you have, you can put it on the chat box. The other mentors will be there to clear it out. So this is there, and tri-state, to, as I said, this plays a very important role here, especially because if it's not there, every time the adder will be putting its output on the bus. We don't want that to happen. Yeah. So, any doubts till now? Yeah, where's the. Let's make this also 8-bit. Let's keep an output here. Yeah. So, by the time, let's name this as well. This is A, and the two operands basically A and B. Okay, B. So this is going to be our output enable, and this is going to be the sub and add, basically to decide whether it should add or subtract. I guess this should be 1. Yeah, this is supposed to be 8. Uh, uh, yeah, just, yeah, so now we should be good to go. So let me quickly explain. Wait, does this? Yeah, again, it's. Just be careful with the. Okay, so so as you can see here, this is the 8-bit adder. One input will directly go to the adder, and here this is where we decide, right, whether if it's an addition or subtraction. So at that time, so this is basically dmux and mux. So whatever input you give here, depending on if it's this is the control bit, right? So if it's 0, it's going to pass this data in its first I mean in the its zeroth line. If it's 1 here, so the same data it's going to be passed in the 1 bit. Again, here in the mux part, if the control signal is set to 1, whatever data is there in its 1 bit line, I mean one this last line, that is going to be passed as its output. If it's 0 here, uh, you know whatever is there in this particular line, that is going to be passed. So if I just want to add, I'll keep it as 0. So if this is 0, uh, directly adder gets its A, and then if it's B, this B is going to be passed in this line, and since again it's 0 here, this is going to be selected and it's going to be added, and if it's 1, output is going to appear here, or if it's 0, it's not going to. Then in similar way, if you want to subtract it, I'll just keep it to 1, and since it's 1, this B thing, this B data, it's going to be passed in the uh, uh, 1 line. So here you have the 2's complement, right? So as I mentioned before, if you have to subtract, you have to just take the 2's complement and add it. So that's what here you have the 2 complement. You get the 2 complement here. Again, you select it and you send that 2's complement to adder. It's going to add, and here you have your subtraction output. So this is how you build the adder subtractor thing for this. Any doubts till now? Any doubt how the circuit works? Let's name this out. Yeah. Any doubts? Let me know. We can put this circuit here, and we'll be among the 8 blocks. We'll be done with the 2 blocks. That's pretty awesome, I guess. Yeah. So let's save the circuit, as I mentioned before. Okay, just a second. Okay, when the program counter is saved, this was saved, and let's put our circuit here. Insert sub circuit, adder subtract. We are okay. We might want to flip this. That's because we'll make this better as to our we saw that we want A gets its accumulator from the above, and B, so just that it fits in with here, and these two here, and output it's because this side. And let's move our title a little below, or we could, since we know it's an adder subtractor. Yeah, click save here. I guess, yeah, this is reflected. Cool. So output, you will be putting it here. Yeah, and you can give the inputs here. Let's make this left. Yeah. Yeah, so what we have to do is, again, we have to split this up since it's 4-bit and 4-bit. Take a splitter here. Since it's an 8-bit and 8, we want it as 4 and 4. Yesterday it was here, and I want to flip this. So, this, and let's give 3 to this. Yeah. Okay. So, yeah. So this is our circuit till now. We can, yeah. So you have built the 2 blocks here. We can.
Hey everyone, this is Kanda here. So it's great that you have built 2 of the blocks, and we'll be moving on forward with 5 more blocks now, and we'll do it pretty quickly because all of them are registers. Namely, it will be MAR, that is memory address register, and instruction register, that is IR. We'll be building the output register, B register, and accumulator. So these are the 5 registers which we will be building now, and that's crazy, right? That is 2 plus 5 equals 7, and it'll be just one more. That will be the memory, and then we'll be done with our computer, right? So let's begin. I'll just share my screen, and before that I'll just refresh the circuit was, so that all the changes Pratyusha made are reflected to me. Okay, give me a second. So yeah, that's cool. There's a slight mistake here. I just want you all to correct it. The clock shouldn't be given to the bus. Okay, so it was just to bring those 2 lines there. Let's just delete that part. We don't need the clock to be directly connected to the bus. Okay, and instead, what we'll do is I'll just move all these down. I'll take output, choose the output. Okay, and then place it here. And then I would say open Control C and a Control V. We'll just connect these to the bus. You can change the orientation to down, and the same with this one too. That is down. I wanted to connect this and connect this and make it a 4-bit one. Okay. Yeah. Just go to the properties and increase the bit width to 4, and similarly the other one. 4. Let's move it this way. Okay. So that should be fine. Now this totally looks like the 8-bit width bus, right? Now we'll begin. Let's see what and all do we need. First, let us go with the MAR. As Pratyusha told, MAR is nothing but memory address register, which is a 4-bit one because addresses are of bit width 4. So that is the only 4-bit register which we'll be using. All other registers are 8-bit because we are building the 8-bit computer. So let's go for it. Let's choose circuit elements and search for D flip-flop. Okay, and keep it anywhere you want. Now, I'll just show you the huge computer which we built, right? And I'll just give a brief thing why it works and why everything is, why everything makes sense. So MAR, you can see its only job is to take the address from program counter and apply it on the memory, right? So that memory can do a read operation. So that makes it clear that output of the MAR and input are fixed, right? Output should go, that is output of the D flip-flop here. I'll just change the bit width also, make it 4 so that we don't forget it later. Okay, so its bit width is set to 4 and its output will go to the memory. I'll just leave it here because we'll be building the memory later. So that is not yet, we'll not be looking into that yet. As of now, we'll be building registers and its input will come from the lower part, that is lower bits of the first 4. This is like it starts from here to power 0, 1, 2, 3 and goes on till 7. So this one will be connected to the lower half because the lower half contains usually the addresses. So you can connect it anywhere there. Okay, so that input and output are taken care of. Now all we need to do is give clock to it, right? I'll just take the clock and extend it everywhere so that all other components which need clock we can use it, right? I'll just show you briefly. So anywhere we need, we'll just pull out from this and then use the clock wherever we want. Now, as I said, we'll just take the clock and give it here. Zoom a bit more. Okay, so that's clock done. Now, only 2 things are left. That is, one is the asynchronous reset, which will be given from the clear one. Okay, the clear will clear the whole circuit. When we build the whole computer, if I just press clear once, everything will be back to 0, right? So for that, so each of the elements should be connected to the clear one, right? And the only thing left here is enable signal. Now, enable signal is a part of control input. Okay, so that when we build the control sequencer, it should go there, but for now we'll be doing it manually. So I'll just take and give an input here. Search for the input, please. Okay. So go to the input, keep it here. You can change the direction also. I'll just make it up. Okay, and then connect it with this. I would request you to name it as I name it so that there is no confusion. It is an active low register. That is input. Okay, I'll just tell you. Most of them you've seen tri-state registers, right? You give an enable. If it is 0, it is not enabled. If it is 1, it is enabled. But for due to some reasons, due to practicality of the ICs or the chips which you use, the manufacturers build it with active low signals. So this is an active low signal. So what I'll do is its input. Okay, just give me a second. I take it out. I have to make a small change. Give a not gate. Okay, search for not gate. Get it here. Here, change the direction again to upwards, and then connect the input here and put the output to the enable signal. Now you can name this as it's LV underscore MAR. That is, tilde represents the negative, that is active low, and LE is for loading the MAR. Okay, so whenever the signal given is 0, it will make the MAR high and then it will load it into MAR. So that's how this works. So yeah, lo and behold, you're done with one of the registers, right? That's how you build the MAR. Okay, so just a second. Okay, we'll see that we'll name everything later. So that's the MAR done. Now the next one which I wanted to build is the instruction register. Now let's build the instruction register. How do you do it? Same old process. Go for the D flip flop. D flip flop. Take it and keep it somewhere kind of below. Okay, so that we need space for memory here also. So let's build the D flip flop. I'll just zoom it back in. Okay. I'll extend this below so that we use it properly. Okay. Yeah. Okay. So I'll just change the bit width back to 8 because instruction register is an 8-bit width register. Okay. So now, what does IR do? It first of all, the memory needs to do a read operation. Okay. So that instruction is fetched from the memory and it goes to the MIR and all the processes happen. And now instruction register holds the current instruction which is being executed. So it has to be 8 width as we know. So that is done. And its input, okay, its input should be splitted from the bus. Okay, I'll show you the proper working of splitter this time because many of us couldn't yesterday. So the input comes from the higher and lower nibbles of the bus. So let's do that. Okay. Now to use a splitter, search for the splitter. Okay. Some of you got it, some of you didn't. So that's not an issue. Got it. Now, there is a pop-up which comes, which will not be shown to you because I'm sharing my screen. I mean, it will be only shown to me. Enter the bit width as 8, okay? And press OK. It should ask you enter bit width split, okay? Now, for example, if I want all the 8 bits split separately, so give 1, space 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 1. So that is 8 times. So then, now if I press it, you can see it, right? It gives me the 8 bit width. So you have to press space in between each of them so that you don't, get error. If you don't, you'll get some random thing. I don't know, not yet tried. Okay. So you can delete this for now and get it again. Give input as 8. But we need to split it into two halves of 4 and 4. So what you do, 4 space 4. Okay. So press that and you should be getting this. Please let me know in the chat if you've got it. Okay. And then I'll move forward. Yes or no, quick yes or no, please. Were you all able to access the splitter? Yes. Okay. Great. Anytime, any other question, my team will be there to help you. Please let us know. Okay. Now that is the splitter done. You have to connect the splitter to the bus. So the lower half goes to the lower one, and upper half goes to the upper one. So that is the output. I'm sorry, input taken care of. As I said, you have to give the clock to. So just give the clock, okay, and again enable and asynchronous reset. As I told, asynchronous reset has to be given from clear. I'll just take the clear and extend everywhere. Okay, like this. I'll just extend this way below so that anybody can use it. Okay. Now the clear signal has to be given to the asynchronous preset. So let me do that. We'll take it from here and give it here. And let's see what has to be done with the enable. So enable signal is again a control input. So what I need to do, enable, take it here, and it should be connected to the NOT gate again because it is designed as an active low signal. So search for a NOT gate, get the NOT gate, keep it, orientation is upwards, and take the signal from this and give an input to this. Okay. Give an input and then change the direction again to upwards or not. It is totally up to you. So that's done. And now this was about the input. Now all I need to do is the output. Output again goes back to the bus. Okay, but there is a catch here. So there are two ways the output is split. One which goes to the bus, and anything from any circuit element, if it goes to the bus, it has to go through a tri-state register. We discussed that many times. It is only because we don't need contention at the buses because some data will be flowing in the bus anywhere. We don't want this to go at abrupt times and then do competition there, fighting, etc. So we don't want that to happen. Only when we enable, only then the output should go. Just take this output, connect it with the tri-state. Just search for tri, and you will get the tri-state register. tri-state buffer, I'm sorry. And then now, since this output is also an 8-bit, before that, just give me a second to split it again. I'll just take the splitter again. Enter bit width as 8, okay, and 4 space 4 will be the bit width split. So you should be getting this again. And just keep it for now. And then now, yeah, so let's not mess it up. Now the lower half will go, since it's instruction register, it has to send the address back. I need to pass it through the tri-state register. Okay, so search for tri, just a second. So that's here. Let's keep it below. Wire dangling there. Lower half goes to the tri-state, which goes to the lower half. Always a match lower half with lower half, upper half with upper half. Lower bits, upper bits, right? So that's one part done. Now, the second part has to be given to the control sequencer. Okay, so I'll just leave it at that. Fine. Yeah, I'll just need to take care of the bit width. That is, its bit width. You can see 4. It is split into 4 and 4. So obviously the tri-state, this should be 4. Okay, and let's check if I have messed up with bit width anywhere else. I think others are fine. Now back to the chat. Anyone has any questions until now? Are you able to follow? A quick yes or no, and then we can move forward again. So yes, it is looking a bit complicated now. So I need to know at every point whether you're getting it or not. Okay. A small yes. Okay. Thank you. So that is the IR taken care of. Okay. So we just have to name it. So that's one more thing. I need to name this. Kindly name it as I say. It will be named as, go for the tilde again, load IR. IR is basically instruction register. Please do that too. Okay. So it's named as LDIR. This, you can see this not of LDIR, not of LDMAR. So all of them, we'll be removing these and giving it to the control sequencer, which will do it automatically. For now, we have to do it manually. So I'll leave it as it is for now. Okay. And yes, we are done with this. All we need to do is give an enable signal to this too. Okay, so that's again a 1 bit. That is search for input again. Go for input and connect it with this. I'll just change that direction up and then yeah. Again, so this I'll name it as. And give me a second. I have to name at each and every point. Okay, this will be LD not of. I'm sorry. Build IR out enable. IR out enable. Please name it as IR out enable. And can anyone tell me what mistake I made here? If it is IR out enable, I should give a not gate again. So that is one thing which I missed. You can delete this and give a not gate. I'm sorry, not gate. So yeah, that's the point, right? We make mistakes along with you and correct it as we go on. So just invert it upwards and give it to the enable. Give it here. That's crazy. We are done with 2 more blocks. That is instruction register and the MAR. Right now, all we have to do is 3 more, and they are very similar and very simple too. Okay. Any questions until now? Any more? I just haven't checked the chat. I'll wait for 10-15 more seconds. Any more questions? Please let us know. We'll get it cleared. I know I've been a bit quick in doing this because we are slightly behind schedule. So please do it. I'll just zoom it for you so that you can see. Yeah. Now, to save time, all we can do is we can start copy paste stuff here. So like how we do in exams. Okay. So I'll just copy this and start pasting. Now all we need is an accumulator, a B register, and an output register. Let's begin. I'll just paste one here, and another here. Okay. So that's three registers done, and all of them are 8-bit. I'll just zoom it for you. Okay. Make this 8-bit. 3, 4, 5, 6, 7, 8. This is also again 8-bit. Okay. Let's move a bit quickly. I'm sorry to do this, but we have to. Okay. Yeah. So we have three registers. Now let's go to accumulator. Now, what does accumulator do? It takes input that is an 8-bit number from the bus, and then it stores it and then gives it to add subtractor. And after addition, it will take it back and put it onto the bus. The bus from it will go down, and then output register will take the final answer. So clearly, we need to split this again, right? I'll just take splitter again and just copy the paste from here, copy, and then I'll just paste it here. I'll get the splitter, very similar, and then I'll just change the orientation here. The direction is right, so I'll make it left. Just a second. Yeah, so that's how I do it. Now, its input is given from the bus, as I told you. So connected to the input, lower goes to the lower half, upper goes to the upper half. Yes. So yeah, we are moving very quickly. Okay. Now, the output of the accumulator again is split. Okay, so we'll just take it like this. One of them goes to the adder subtractor. So I'll just give it as. Okay, give me a second. I just told right. It will supply one of the numbers to the adder subtractor so that it can add. Now, what I need to do, I need to take the same output again. Now, why am I doing this? Because after the cycle, after it adds, the result is temporarily stored in the accumulator, and that accumulator puts it onto the bus, right? So the output has to go to the bus, and it has to split and then go again into higher and lower nibbles. So I need to split it again. So let's do that. I'll see this. Second, take this and I'll copy the splitter again. Paste it and take the direction this way. Okay. Control C and I'll control V. So I get the splitter here. Okay. Second. Just give me a second. Okay. So before I split it, I just need to do one more thing. That is a tri-state buffer, because anything that goes onto the bus has to be given through the tri-state, right? We have discussed that before because we don't need contention. I've already told this numerous times. So have my teammates. So I had forgotten that. So search for try. Okay, go for the tri-state. Connect to the tri-state. Okay, and then take its output. Give an enable. We'll just name it in a second. And yes, please don't forget the clock. For our convenience, I'll take the clock from here and then put it everywhere. Literally, we need the clock everywhere. So I'll just stretch it way longer. So do I need the clear? Take it everywhere. Please do this too, so that we will take it wherever we want. Okay. Okay. So that's done. We'll zoom out so that you can see. Now we were here. I need to give an enable for this also and an enable for this. Clock comes from here. I think this was a clock signal. Clock this and asynchronous with this clear. you following? Yes. I was probably quicker, but yes, we need to do this. Now, the input to this has to be again passed through the NOT gate, because I'll just name it for you before that. Go for NOT gate, search for NOT, keep it here. I'll just change its orientation to down this time. Okay. Give me a second. It's up. It's fine. Anywhere. Okay, it should be down. I was right before. Now it's input. Give an input. Search for input again. Yes, it is a tedious task, but we need to do this. There. We are done. Now all we need to do is take the splitter as I did before. I had forgotten the try state. So take the splitter again, search for, you can just copy paste from anywhere we want. Take this and control C and the control V signal to do it. Connect it to the output. And yes, now as I said, output of the accumulator should go back to the bus again so that output register can take it later on. So what I'll do, I'll just take the higher half. Okay, higher will go to the uh, higher half of the bus, and the lower one will go to the lower half. Okay. Oh yeah, there is. Are you clear till now? I hope you are. I'll just name this. It is out enable. So see, clearly I'm not giving a till here because it should be an active high. Yes, so I've named it, but I put a NOT gate. So that was my mistake. So I'm sorry for that. It should be deleted and you can give it directly. Just put it back here again. It was an active high signal. I had forgotten that. So you can give it directly. Okay? So that's 3 registers done. That's crazy. Yeah, I'm missing the enable. Yeah, enable to the accumulator is a different signal again. So I'll just name it here. Take the enable, give a NOT gate. NOT gate. Search for the NOT gate. Keep it here. And yeah, just connect this and this. This can input to that too. Registers, dealing with these registers is all about giving input and NOT gate if required. It was active low signal and then naming these. So please name this enable as filled. I'm sorry. Filled. Name will be load accumulator, load ACC. The names all make sense, right? So I'll just label direction to the down so you can see clearly. So that's 3 of them done. Now let's move on to the 4th and the 5th one. Okay. Another quick yes or no if you could follow these 3 registers. I'm really sorry I had to be a bit quick. We have a little more things on our table yet. So quick yes or no from anyone so that were you able to build this? The screen is still being shared, so you can take another 20-30 seconds to just get it done. In case you're not able to build and you're stuck somewhere, you can at least draw it on your paper somewhere, just quick connections everywhere, and then you can build it on your own later to see it working. I would recommend that too, if in case you're doing it. Pen and paper is really good. Anything, whatever suits you, but just don't sit idle. Okay, so we'll do it. Let's do it practically, and then that gives us the feel. Now, after the accumulator, we need to build only 2 more registers, that is B register and output register. Now let's build the B register. Consider this to be the B register. Its output has to go to this, as you very well know. Just give me a second. I'll just take this property. It continuously drives. Okay, the adder subtractor. So output is done. So we just took care of the output, and I'll just take care of the clock. You can do all these first. It's fun, and its asynchronous reset is given to the reset, and yes, yeah. Everywhere the output of the registers, right, they're all 8-bit, so you have to make those also 8, so please don't forget those. So that will be done. And have I missed anywhere else? So these are all single bit. Yeah, this 8-bit, please make sure. And there shouldn't be any contention anywhere. Just make sure all the bits are proper, and this is fine. I'll just reconfirm everywhere. This is 8-bit, that should be okay. Its output is 8-bit, that should be okay. Tri-state is 8-bit again. I'll just take it should be okay. Yeah, so I think it should be fine. Other we just confirm with other two registers also. Oops, I'm sorry. Put here just in case. All these stray wires, we will just remove those. Properties, it's 8-bit. This is splitted, so it's 4-bit, 4-bit. So I think it should be fine. Okay. So yeah, we'll just take now. We'll get on with the with building the B register. So input to the B register, right? Input to the B register is again taken from the bus, because the memory dumps the output, that is whatever value has to be subtracted from the first one, onto the bus, and the bus will take it, and B register will take it from the bus, right? So its input has to be again split. Okay, so take the splitter. We'll take this type of splitter because it is oriented this way. Just copy it, paste it. So that's done. Lower goes to the lower. Did I do it? No. Yeah, lower goes to the lower, and higher one goes to the higher. So that is input to the B register done. Okay. Now all we care about is the enable. So enable signal is again, it's an active low segment. So take it below. An inverter is required that is not gate. Search for the not gate. Keep it below this and connect its output. And then input is a single bit input. So search for input, that's already there. Connect it. Name the input as I say. Okay, the input will be named as till load be rich. That's basically what it does. Okay. Put it down anywhere. I haven't connected it yet. Give me a second. Direction is right. Connect this, and there's a stray wire. I'll just oops. So naming of this, I'll just change it down so that it doesn't. Okay, there's a stray wire there. Give me a second. Okay, I'll take another one. No issues. You cannot get. Keep it here. Connect it to this. Zoom in very much. I'll take this direction to the right, and then connect it here. Okay, that should be done. And naming of this, you can keep it on. So that's finally done. Okay. Yeah. So that's one thing. All we need to do is check the output of the B register. Are you all following me? It's all been me talking and you listening. I'm not even sure if you guys are listening anymore. Yes, a quick yes from anyone. Okay. You guys are following? No? It's just a flip-flop being converted into a register, and based on what logic is, it should go to the bus or it should go to adder subtractor. Depending on that, we choose the tri-state or not. If tri-state is, if you're dealing with a bus, if from any circuit element, it has to go to the bus, it has to go through this tri-state because we don't want contention anywhere. The tri-state will enable, only then it will go onto the bus, we dump it to the bus. Yes. So that's the only logic there. So don't get too much tensed when you see, all the tri-state registers everywhere. So that is done, and all we need to do is the output of the B register, which is done, and yeah, so that's finally done. Now finally we come to the output register. So we are almost at the last stage, barring the memory. So that's 8-bit. We've already selected it. Now let's check what happened to the output. So I'll take the output, just keep it there for some time. Clock goes to the clock. Okay, that's clock done, and asynchronous goes to the asynchronous feature. That is clear. Are you clear? So that's how it is. Okay, fine. Now we need to see what happens to input. And yes, there is an enable. Enable, take it again. It's an active low signal. So take a NOT gate, take it here, select the input, go for an input. We'll just move through this quickly, and I'll just name this, label it as till, search field, and then output because it's out, and then let enable register. It's enabled right here. Yeah, it's LD out range. Okay. LD. Okay, I'll just orient it to down. Okay, there's a mistake again. Hold on. Orientation is towards right. This goes as input. Now I'll just label it downwards. What's happening? Okay, give me a second. I'm choosing the wrong one. Give me a second. Give me a second. Yeah. We are done. So we took care of the clock, asynchronous reset clock, etc., and the enable. Now, how do you get the input to the output register? Obviously from the bus, because bus is feeding literally everything here. Okay, so again, take the splitter, choose the same splitter. You can choose this, copy, and just control V. Okay. That's connected. Lower goes to the lower one. Okay, and upper goes to the upper. You took care of the input. Now all you have to do is take the output. I'll yeah. You can take a hex decoder, okay, hex display. As I showed you before, right? This is one of the main parts. So I'll just keep it here, and I'll control C and control V it one more. So I'll just keep both of them next to each other. Search for hex. Okay, you'll just get it. Hex display. It's called as hex display. Hexadecimal. Whatever hexadecimal value is coming, it will just display it in the decimal value. Okay. So you have to split this again because you need to split it into again lower and upper halves. Take this type of splitter, copy it, paste it. Okay. Okay. Just take this part, delete it, and join it here. So obviously lower goes to the lower half, that is here, and upper goes to the upper. You can just see the red light just glows up, right? So that's great. You just built most of the computer. You see, you are feeling happy right now, right? We almost are done. We just need to build the memory, and it's done. And give me a quick yes, and we'll move on to the next one. Yes, someone, you could build this. You need any help, any queries? You're stuck anywhere? On the contentions and errors, we'll see that later, but I wanted to build the circuit first and then we can take care of the errors. Okay. Unless and until you have any doubts, we can move further. Yeah, I'll just don't forget to save because you might lose it. Okay. So I'm just saving this. You'll get a green message here. We have saved your SAP1 workshop thingy. So do that. Okay. So yes, we are done with most of the thing. Congratulations that you've made it this far. It's a really great deal. Even we were very happy when it was done. Okay. So yes, we'll next go on to the memory. So Ram Prakash, you can take it from here. Thank you all for being with me and listening to me until now. Okay, see you.
Right. So, how many types of memory have you heard of? Right off the top of your head, any examples of memory? Like when you think about computer memory, what comes to your head first? Exactly. So an example for volatile memory, as Rohit said, is RAM. And for non-volatile, you have like ROMs and EEPROMs, so read-only memories, which can be written only once. Like when you manufacture ROMs, you just write them once and you can't change them ever. And there's an EEPROM, which is electronically erasable, programmable read-only memory. So this is the kind that is used in most circuits now. So you can erase it and reprogram it, and it'll still retain that after you've disconnected power and so on. And this is what we'll be using for this computer. You can call it an EEPROM because like we will be able to write it later, like by ourselves, but when the computer is running, you will not be able to change it. So it is a type of ROM. So this computer uses memory in a very special way. And we also discussed von Neumann architecture, right? So it is one of the features of the von Neumann architecture where you have a unified memory scheme. So you can see a grid on the screen, right? So assume this grid is our memory. So each of those cells represents 8 bits. So each box can contain 8 bits of data. So this is literally how much? 16 bytes of data. Okay, so that's not a lot of memory, but that's how much we have to work with this computer. So that's 16 bytes of data, and they're divided in specific manner. So the first 2 rows, they are called the program. So they're reserved for your programs. So that is called the program memory. The lower half is for the data. So like say you're adding 2 numbers and all that, the numbers which you're adding are stored here. So the lower half is called the data memory. So everyone okay with that? So once again, 16 bytes divided into 4x4 grid. Top half is program memory, bottom half is data memory. So how do we access these values, right? So the way you access memory is through an address. So each of these cells has an address, right? So you can see in the top left corners of each box, I've written 0001 all the way to 7. So they are the addresses of the first 2 rows. So now can anybody tell me how the next 2 rows will go, considering the addresses are in hexadecimal? So if I'm writing hexadecimal numbers, how should I name the rest of the 2 rows? Can anyone complete that for me? So at least tell me the next cell, what should it be?
8.
Yep. So 8, 9. And then since it's hex, A, B, C, D, E, F. Okay. So A represents 10, B 11, C 12, so on. So this is how we'll be accessing memory. So if I tell the memory 4, it'll immediately, like you go to that value that is in the cell labeled 4 and then output that, like be ready to output that. Okay, so that is how we'll be addressing memory. So now that that is out of the way, let us actually build it. So I want you guys to get back to your circuits now. So lucky for you, there's already like a pre-built block for ROM in Circuitverse, so that's very convenient. Just refresh. Right, so just search for ROM. You'll get this thing here, this block here. So this thingy right here, so you can see here, this grid is what I made in the presentation. Okay, so this is 0001, so on, 08, 9, 10, 9, A, B, C, D, E, F. Okay, so once you have that, like Skanda said, this output right here should go into the address. So this A stands for address here. So I might just take it around, bring it here. Right, okay, don't think we'll have space. Let me just move this back a little. Okay, so the address comes from the MAR. So you can see this dark green box. So that means that the address that you have input, so it shows what address is currently loaded. So it's a 0. So the dark green box is that showing is 0 at the address 00. Now next, I want you to answer this one. So the output goes to the bus. So what should come before I output to the bus? Quickly, come on. So if I'm outputting anything to the bus, there is one component that must be there. So can you tell me what it is?
Tri-state.
Yep. So let's grab a tri-state right here. So tri-state, and then, okay, this is a 4-bit one. So make sure your bit widths are correct. And again, as usual, we need to split it. So I'll take it from here. So just copy pasted it. So, okay, it's a bit too close. I'll move it back. Oh, something. Right, so the lower nibble goes to the lower bus, and then this goes here. Right, so what's left is this enable signal. So I'll take this. Guessing that's also an active low. So we'll grab this inverter, put it here, right? So another thing, you see this EN here, so that's like the built-in output enable. That's not very convenient to use, but so the way this inbuilt circuit works is if this is set to high, that's when you'll get the output on like here. So otherwise it's going to be like an unknown state. So I'd rather just put this as 1 fixed. So if you guys just search, go to the input tab in the elements, you'll find power. So what I recommend doing is just like hooking it up to power so that it's forever on. And this is the signal that controls the output to the bus. I'll just put this in. Okay, so that's it. So this is the memory arrangement for your SAP1. We just need to do one more thing, that is name this. So it is again active low, so it starts with a tilde and memory output enable, right? So that's the name of this signal. Let's see, move it to the left. Okay, so that's all. So that's it. So that's how the memory is going to be hooked up in this computer. So I'll just zoom in on this part here. This output comes from the MAR. This is set to the power input. The output goes to a tri-state that is split for the bus. The enable is active low, and it's called tilde mem underscore out underscore enable. So memory output enable. So I guess in the meanwhile, I'll probably show you a demo of how this actually works. So you guys don't need to do this per se. Just create a temporary circuit, right? So just to see how this works, right? Okay. All right. Okay. So now you see, enable is 1, 0, 0 selected, address is 0, 0, 0, 0. You get the output as all zeros. So now I can actually change this input. So the way you change data in this memory on circuit bus is you just select the cell you want and then type in the value in hexadecimal. So yeah, an 8-bit number, when you convert to hexadecimal, you divide it into like pair, like groups of 4. So the last 4, then 4, 4, 4, and so on, and convert the individual ones to hex. So let's say I want to represent the number like 8 ones, 1, 1, 1, 1, 1, 1. So the way I convert is divided into 2, 4, 4, 1, 1, 1, 1 in hex is F, 1, 1, 1, 1 in hex is F. So F, F. So if I disable this and then click on it, FF. So you can see it's changed to FF. If I do this, there you go. So I can change the address and show you. So if I just say put it to 1, so you see the dark green box is moved to 1. So this is the address 01 and the data is 0. So we'll just get back. Right, so this is where we make a big leap, right? So now we're done with all the hardware stuff, the low level stuff. We've wired it up and we have like a basic structure ready. So now we are going to move on to something that's very, very important. And it's a big milestone that we're achieving. So now we're moving on to the instruction set. So now we're moving into the programming phase of this workshop. So each CPU or microprocessor, microcontroller, whatever is there, it's going to have something called an instruction set. That is what all operations it's capable of. So when you program it, it'll have a set of instructions that it can perform. So let's say you have like your Intel CPUs, like any modern CPU, it'll probably have instructions to do floating point addition, floating point division, multiplication, stuff like that. So they define the capabilities of the CPU. And they are usually what you reference when you're writing in assembly language. Okay, so this computer has a very small set of instructions. Like I said, it's capable of doing only addition and subtraction, right? So we'll just start with the first instruction, or rather, we'll start with the format of the instruction. Like I said, this is an 8-bit computer, so all the instructions are also 8 bits. Again, we have divided the bus into 2 4-bit sections. So here you'll get to know why. So the first 4 bits are reserved for what is called the opcode or the operation code. So this defines what is the, so this is essentially what tells the control unit what all things it should do to get the output that we require. So for example, say we want to add 2 numbers. This is the opcode is what tells the computer that, okay, you need to perform addition. So the control unit will do all the necessary things to perform addition. Okay, so that's the opcode. The later half is the address of the operand. So you are performing these operations on something, right? Some data. So the latter half represents the address. So note that I've emphasized address. So it is not the data itself, but where the data is. So if you're familiar with programming, let's say in C or C++ or something like that, you've heard of pointers. So essentially what the last 4 bits represent is a pointer to where the data is. So the SAP1, like we said, is an 8-bit computer. So the instruction set is also limited to 8 bits in size. We divide the 8 bits into 2 halves. So the upper half, so the left 4 bits are known as the upper half because they're like the higher part of the bits, so like bit value. So the left half is reserved for something called the opcode or the operation code, which defines what is the operation that should be performed by the CPU on the right half, which is for the data. So the right half represents data, left half represents opcode. And the right half specifically doesn't represent the data directly, but it represents the address of the data. So let's say I give, say, 0. right? In the, okay, not 0. Let's say I give like 10 or something in the address. So what that means is I'm not using the value 10, but what the computer will do is it will search for, go to the ROM, go to the address 10, some value is going to be there. It will take that value and perform the operation on it. So now we get to the SAP instruction set. So the first instruction opcode that we have is called LDA. So it stands for load accumulator, and in binary it's represented with 0, 0, 0, 0. So that left half of 4 bits are there. If you give all zeros there, it will mean that your the opcode is LDA. And what this instruction does is essentially in the right half, whatever address you have given, it goes to that address, takes the data over there, and puts it into the accumulator. Okay, so it's as simple as that. So it loads the accumulator with whatever data you give in the address. So this right half, so whatever address I give there, it's going to take the data at that address, put it into the accumulator. So by the end of this instruction, the accumulator will have the data pointed to by the address. Okay. So next is the addition instruction. So add. So what this does is just adds the data present in the accumulator with the data present in the address that you specify. So if I give add and let's say 9, it goes to the address 9, takes the data in that location, puts it into the B register. Then once you put it to the B register, you'll have something like in the accumulator, right? So it adds those, puts it onto the bus, goes back to the accumulator. So at the end of the add instruction, the total sum will be stored back into the accumulator. So the accumulator data will be lost and it will be replaced with the result of this addition operation. So next, obviously it's like complement, so it's subtraction. It is identical to the addition instruction except that you perform subtraction and you store the difference in the accumulator. So everything is the same. Whatever address you give it, it goes to that address, takes the data, puts it into the B register, and then the operation performed is A minus B. So if A is the accumulator and B is the B register, you do A minus B and then put it back into the accumulator. Okay, so that's the subtract instruction. So next is an instruction called out. So this instruction is pretty special because it doesn't really care what the last 4 bits are. Okay, so what's important is only these first 4 bits, 1, 1, 1, 0. So what this does is it instructs the computer to take the data from the accumulator and then move it to the output register that you just built. So essentially, if you want to see the output of the calculation, you need to give this instruction. It doesn't take any address because there is only one place it takes its values from, that is the accumulator. So it doesn't really care what bits are there in the last 4. You can give whatever you want and it's just going to work. Okay, so that's the output instruction. And then finally, you have this instruction called halt that just terminates the program and tells the computer to stop everything and like literally do nothing. So if you give the halt instruction anywhere in your program, whatever comes after it is not going to happen because the computer has literally stopped doing everything. Okay, so everybody clear with the instruction set? So that's all. You just have 5 instructions for this computer. So all those control bits that you guys were setting with specific names that Skanda and Pratyusha told you to, all of them are going to influence, depending on the opcode, what is going to happen in this computer. Okay, so now we are essentially set to write programs for our computer. So give you guys a hand. So we have actually reached a point where we can program a computer that we just built. So that's a real big milestone that we have achieved. So before we do that, let's just go through a few guidelines on how this programming works. So you always have to start with the LDA instruction. So I'll tell you why. See, when you turn on the computer, the A register will essentially contain a 0, or if it's not been reset properly, it will contain some garbage value, right? So you would essentially want to start by loading something into the accumulator, unless you're sure that it's going to be a 0 and you don't mind because it's a 0. So you start with the LDA instruction. You have to end with halt. So when you want the computer to stop, you need to end with the halt instruction. You forget to put the halt instruction, your computer is just going to be operating like gibberish, like whatever data is there in the memory. Like if you've done C programming, I guess you would have probably encountered like junk output, right? You're essentially going to get that. You're going to get junk output from memory that you really don't have control of. Like here it's a really small block of memory, but you really need to tell the computer to stop, otherwise it's not going to know when to stop. So any programming language that you learn, it has an equivalent for this halt instruction. So at least even in like it will have it in the assembly language level. So everything gets compiled down to assembly at one point in time. So at that stage, there will be a halt or like a no operation or like a do nothing instruction for any CPU processor computer out there. Okay. And like I said, all data goes through the accumulator. So you need to use the accumulator like an operand as such. Okay. So now that we're ready to program, let's go through a simple example program. Okay, so this is not going to take long. Just going to add two numbers. Okay, so if you can see the grid there, I've like highlighted the bottom half with a different color just to distinguish it from the program memory. So the bottom half is the data memory, and the first two cells also I've highlighted because this program is going to add the values in those two addresses. So quickly, I want any of you to tell me what is the what are the addresses of these two cells? So can anyone quickly tell me what is the address of this cell and what is the address of this cell? So I'll give you a hint. This starts from 0, 0. So this is 0, 1, 2. So what is the address of this cell? What is the address of this cell? 8 and 9. That's right. So like I said, when we start off our program, we need to start with the LDA instruction, right? So that's exactly what we're going to do. LDA, and then I've given this 0B prefix just to tell you that it's a binary representation of 1000. So what's 1000 in decimal or in binary? It means 8 in decimal, right? So it essentially says, take the data that's here, put it in the accumulator. Okay. So after that, we need to add. So the next instruction is going to be add, and then the address of this, which is 9, so which is 1001 right there. So what this does is takes the data, puts the data, whatever number is there here in the B register, adds it to the accumulator, and then replaces the accumulator data with the sum. And after this, I think I've missed the instruction. So I actually missed two instructions right there. So after this, you need to output the data because you're not going to see anything unless you use the out instruction. So let me quickly add it, I guess. So it's going to be out and essentially nothing. So I'm going to put X, which means don't care. So you don't really care. And then we need to end with halt. So essentially this is the program, right? So we'll see how this data is represented, like how are we going to write the program. So we know the top half is the program memory, right? So the LDA instruction is stored as 0, 8. So can anyone break it down and tell me why that first cell there has 0, 8? So 0, 8 represents data. So how do you think the instruction LDA 1000, which is 8, translated to 0, 8 in hexadecimal? 000 opcode, 8 data. Wonderful. Awesome. So similarly, for the add instruction, it's going to be 2, 9. So the opcode, if you remember, for the add instruction, okay, not 2, I think it's 1. Again, I apologize for the mistake. Let's just take a look here. It's 1. Okay. So, so 1, 9, right? So 1, 9 just tells subtract, no, rather add the data in the address 9 with the accumulator. Next comes the out instruction. Probably missed that too. Okay, so the out instruction, let's see, the opcode 1110, which is E in hexadecimal. So 14 is E in hexadecimal, so it's going to be E. I can literally give anything I want here, so I'll just give 0. And then finally it's going to be halt, so it's 1111, which is F in hexadecimal. So F, and I can give whatever I want to give 0 again. So essentially this is how the program is going to be stored in memory. So all you have to do is, I showed you that RAM block, right? ROM block. You'll have to click on these and then like store them like this. So 0, 8, 1, 9, click on this, type E0, click on that and type F0. That's it. You have to program your computer. So how many of you have followed me until this point? So how many of you have understood the structure of that program? So if you haven't, I'll gladly repeat anything that's required. So have you guys understood, or should I repeat? So the program is this. This is how the memory looks. So let's say I have 5 and I have 1, right? That's the data there. The output will be 6. Cool. So that is going to be the end of today, I think. If you guys really want to stay back a little longer, I can actually show you this on the computer you built. We can actually manually set the control signals and see it in action. We'll be tackling the control unit tomorrow, so we'll be automating the whole process and finishing it up tomorrow. But do you guys want to take a sneak peek at what your computer is capable of now? We can manually set the control bits and make the instructions like make it happen. So you want to try it now? We can definitely do it. So if you want to, please put a yes in the chat. We can actually try out the program that I just explained on your computers. You guys can try it. As an assignment, you can probably write any program you want that fits into these 8 bytes. And you can come with your own programs that you have written tomorrow, and we can try them out on the computer. Okay? So thank you everyone for staying this long and listening. I really hope you have learned something new. So tomorrow is going to be the grand finale of all of this work that you guys have put in building this circuit. So we are going to go through the control logic, and that's it. Once we wire that up, you can just turn on your computer and it will do the calculation and give you. Before you leave,